consist. So we're going to continue talking about transformers today and how the transformer architecture works. We have a sequence of words. So we've transformed all the words into word vectors. We pass them through a sequence of transformer layers. What does a transformer layer consist of? Each transformer layer consists mainly of two parts. So we pass our sequence of words through one layer, then through another identically structured layer. And we do this k times until we get to the final output layer where we're going to do some stuff with it, like predict the next word, or do just a classification, a sequence level classification, like what type of document is this. We'll talk more about what happens after we're done with the final layer. But what we're going to be focusing on to begin with today is what's happening inside of each individual layer. Now, we've covered attention. We spent 1.5, I think, lectures talking about how attention works. What attention says is that each word becomes a combination of all the other words in the sentence. So the most important thing about attention is that it mixes words together. After you are done with attention, each word representation is now a mixture of all the other word representations. And we define mathematically how that happens. So let's look inside. This is gross. Like, well, who's leaving like their, like, I don't know. There's something really good. I think if it was a smaller water bottle that someone had left here, that would be okay. I don't know. Like, how long was that person carrying that thing like around for? Okay, let's ignore that. All right. Let's look inside of a single layer of the transformer and what's happening there. So what does the single layer say? You have attention. We have our words going in. So we have n words going in. That's the full length of our sequence. N vectors, and we have n vectors coming out. We've learned about how we compute each of those vectors. Let's call these new representations, we'll call them A's. A's for output from attention. We're then going to feed these vectors into an MLP layer. Again, this is actually, we're still in the not quite transformer stage of things. So what I'm teaching you right now, we're going to build up to the full model today, but I'm going to leave out a few details for right now. Okay, so we take all of these vectors, we feed them through the MLP layer, multi-layer perceptron. We've learned a lot about multi-layer perceptron. So what does this mean? This is a little bit ambiguous, right? So how exactly does this MLP layer process these vectors? Let's first define what the MLP layer is, because the MLP layer in transformers has a very, very specific structure. So the MLP layer says, we'll call him, we'll let's just start with the output vector, h1, is going to correspond to the first input vector. What's it equal to? It's equal to so this is the full formula. This is the full MLP layer. It's this little equation here. What we're saying is the MLP layer takes in vector A1, the vector corresponding to the first word. We multiply A1 by a weight matrix. Here I'm calling it WMLP1. So it's just a normal matrix vector multiplication. We take a ReLU. So we apply nonlinearity to the result of that. This is a vector now. We multiply that by WMLP2, the second MLP weight matrix. That's it. That's the MLP layer. The general formula is that HI, so just to be clear, after we apply the MLP layer, we get out a sequence of vectors, h1, h2 through hn, one for every word in the sequence. Hi is just equal to WMLP times ReLU WMLP1 AI. That's the general formula here. So what do we notice about what the MLP is doing? Like so the MLP is processing both the attention layer and the MLP layer. They take in a sequence of n vectors. But there's something there's a lot of little differences between these two layers, the attention layer and the MLP layer, but there's one very, very big difference between them. What's the big difference? If you get the answer to this, we can talk about some spicy stuff. Otherwise, no. Yeah. That's a little difference. You're right, there's mathematical differences, but there's a very, very important conceptual difference between how these two layers operate. What did I say at the beginning of the lecture was the most important property of the attention layer? Yeah. It's not that it takes, let's say that a little more precisely, but you're right. It's that the output representation for each word contains information about all the other words in the sequence. Let's contrast that with the MLP layer and what it does. What do we notice about what the MLP layer does? So I have a definition here. HI is equal to this formula. What do you see happening in that formula? Yeah. It doesn't look at the other words, but so there's a slightly more precise way that we can say that. It doesn't look at the other words. So HI only depends on AI. What's that? No, I was just, I think just that the MLP is a function that only looks at one word embedding at a time, that one word representation at a time. So rather than mixing together all the word representations, the function that only takes in, it processes each word separately, the MLP. Very different than attention, which processes all the words sort of together. So the MLP is this fully parallel thing. It says apply exactly the same function to all words independently. So in the transformer, we alternate. If you remember one thing about the internals of the transformer after this class, this is the thing to remember. We alternate between doing two things. In the attention layer, we mix words together. In the MLP layer, we process words independently. One reason why I'm emphasizing this is that there are now non-transformer architectures that work very well for language modeling and other similar tasks. These have been discovered in the last 6 months or so. So they're new, but they work very well. But this property of alternating between mixing and then doing processing on individual words in parallel, alternating between those two things, that's conserved across all existing models. Let me give a bit of an interpretation of what the MLP layer, what we think it's doing. Now, this is an emergent property of the MLP layer, but it's like, I'd say this is sort of consensus in the field now that this is what the MLP layer is in fact doing. So what is this weight matrix here? This is the first MLP matrix. And by the way, so the MLP has, each layer has its own MLP layer, and the weights for the MLP layer in layer 1 are different than the weights in layer 2. So we have attention here, followed by an MLP. This MLP is different than this MLP. The structure is the same, but the actual numbers in the weight matrices are completely different, and they're learned separately from each other. Okay. So let's look at this MLP here. And so let's say that AI, that the dimension of AI is equal to D. Okay? So we have d-dimensional vectors. Each word is represented by a d-dimensional vector. What are the dimensions of the MLP? This is a convention that is used everywhere. Well, we know how many columns does this matrix have? It has D, right? Because we know that this matrix has to be multiplying this vector. So we know there have to be D columns. And the convention is that there are 4D rows. So this is a huge matrix. You could use another number besides 4D, but this is what all models use. It's a hyperparameter that's been optimized. These are huge matrices. Why are these huge matrices? For GPT-3, let's say, okay, so previous generation of GPTs, GPT-3, D was equal to 10,000 or so, maybe 10 or 20,000. Let's say 10,000. That means 4D is 40,000. So this is a 10,000 by 40,000 matrix. So how big is that matrix? So what's 400 million. So just one matrix here has 400 million parameters in it. Okay. So we multiply W1 MLP times A. What's that doing? That is giving us weights. We can think about that as giving us a single number for every row here. So we have 4D rows. It's giving us a single number for each row. So what we get are, we can think about these as by a weight here, I just mean like how important is this row? A higher number will indicate more important. Okay, so we have this vector here. Let's call this vector G. So this is our vector G. We then do a ReLU on this. And we're then going to multiply W2 MLP ReLU of G. So this is a vector. ReLU of G is a vector. We multiply by W2 MLP. So what's W2 MLP? This is another matrix. What are the dimensions of this matrix? What do we know about the number of columns? Number of columns? 4D. Okay, so there's 4D columns, and then the number of rows is equal to D. Because we want to output a vector that's the same dimensionality as the original vector. We're not going to be changing dimensionality of the vectors in this layer. Okay, so we have this new matrix here. So what we've done is we've said, so G contains in it, or G or ReLU of G, whichever one you want to look at, these contain weights in them that say how important are each of the columns in here. The higher the weight a column gets, the larger its contribution to the output of this matrix multiplication. So I'm just making an observation about how matrix multiplication works right now. If the second column gets a very high weight, a higher weight than anything else, then that will contribute. The second column will contribute more than any other column in this matrix to the output. So based on this, the interpretation of what the MLP is doing is the following. The first multiplication here is telling the model what information should be looked up about this vector. The second multiplication is then retrieving the information that needs to be looked up essentially from a database. So each column in this second matrix, each column here, contains facts about the world. Maybe facts about language, facts about the world. For example, let's say that you are trying to, the model is trying to predict Rome is the capital of blank. We're in the process of predicting the blank here, okay? So what the model will do is use this first matrix multiplication to look up, okay, I'm looking for the capital of Rome. There will be a particular index that says, here's where the capital of Rome information is located. It's going to be located in the third column of this matrix. We then do a matrix multiplication, retrieve the third column. That third column contains information about Italy. So we look up, we first say, what information do we need to retrieve? Essentially, where is that information located? And then we go into a database, which is just a bunch of vectors of numbers, and we pick out the correct vector. And this really actually looks like, I'm not going to say this is the only thing that the MLP does, but among other things, the MLP does do this. This has been demonstrated. You can actually go into the model and find out like where the information about the capital of Italy is located. It's like this, this column in this MLP matrix. And if you edit that column in that matrix, the model will now predict Rome is the capital of France, or whatever else you want to perturb it to. Yes. It would what? Sorry, we need to be what? Oh, but it does, because the model needs to learn all of this. So the model doesn't come equipped with this world knowledge. It needs to learn it, and the way that it learns it is through backpropagation. So this is why, okay, when you actually think about this, when the model is reading through text, like giant amounts of text, and trying to predict the next word, what it's actually doing is populating these enormous weight matrices with all of these different facts about the world. It's a complicated library. It's a database. We have like one vector per fact or entity. Yeah. So what I'm describing, right, these equations here, this is how the model runs. This is the forward pass of the model. And then during training and then during testing, you just run the model using the equations on the forward pass. What's different between training and testing is that during training, you're also doing a backward pass where you compute the gradient and you update the weights. But the equations are the same whether the forward pass is during training or not. Any other questions? Yeah. The positions of the word vectors. What do you mean by that? So these are not word vectors in this database. These are not word vectors. These are like vectors that describe facts about the world. Right. The word vectors are the things that are input into the model. Is that? Yeah. I mean, everything. I mean, just like the columns end up just being like numbers, right? And so those numbers all have to be learned. And then like the model being able to maybe there's a question here, like how do we know that this column represents what the capital of Italy is? How do we as humans know that that's what that information ends up representing? And it was very hard to figure that out. And the way that we did it is that we discovered that if we swap this particular column with another column that we think represents the capital of France, then the model starts making incorrect predictions. It's through observing. We do surgery on the model, and then we observe the consequences of that. That's how we figure out that here's the information that is contained here. Yeah. No, so they're not tied between layers. So every layer has its own pair of MLP weight matrices. Well, right, and that's why. So how many parameters does GPT-3 have? So okay, great. Let's do a back of the envelope calculation right now. GPT-3 has what is it? 100 and I'm embarrassed that this number is not just rolling off the tip of my tongue. Is it 135 billion parameters? You should be ashamed of your professor right now. I believe it's 135 billion. I mean, I'm within 10 billion parameters there. So no, 175 billion. Sorry, it has 175 billion parameters. It has around 100 layers in it. Okay. So this is a good calculation for us to do. Let's talk about how many parameters there are in one layer. We've basically talked about all the weight matrices in the model now. There's a few others that I'm not including, but to a first approximation, we talked about all the weight matrices that exist in the model. So per layer, so how many parameters in one layer? What are all of our weight matrices? We have how many in attention? Can someone remind me? How many matrices are there in the attention layer? Yeah, 3. Okay. What are they? Great. We have Q, K, and V. So how large are the Q, K, and V matrices? They're all D by D matrices. So D is the size of the word embeddings. None of the matrices change the size of the word embeddings. So they see a word, they output a vector of the same size. So these are D by D matrices. So that implies that we have D squared parameters per matrix. Okay, let's say the MLP matrices. We have 2 of them, right? We have, what's my notation here? Okay, W1 MLP and W2 MLP. These are either D by 4D or 4D by D matrices. I mean, it doesn't really matter. So let's say that they're 4D by D. So that implies that we have 4D squared parameters per matrix. Let's say that D is equal to 10 to the 4. Okay, so that's 10,000. Let's see what happens. So suppose, well, let's actually, let me do one calculation first before we get to that assumption, which is, so let's add up the total number of parameters. Okay, so total is equal to what? It's equal to 3d squared plus 8d squared, or 11d squared. So this is true at basically every transformer. Every transformer per layer has 11d squared parameters in it, where d is the size of the word embeddings. Where do we see the relative contribution of the parameters? 8/11 of them are in the MLP. That tells you something. What it says, I mean, look, like I'm trying to emphasize that deep learning is stupid, and stupid intuitions get you like very far. MLP has 8/11 of the parameters probably means it's twice as important as approximately twice as important as the tension layer. That's a pretty good intuition to have. Okay, so we have 11d squared parameters per layer. Let's say our number of layers in GPT-3 is around 100. So let's say num layers. Let's set it to 100. I mean, I can set this to some other number. Let's just say it's 100 for right now. And let's say d is equal to 10 to the 4. So with these assumptions, how many parameters do we have in our model? Okay, so let's see. So what do you do? You just basically multiply everything together, right? You insert d into this formula and you multiply by 100. So it's going to be 100. So 10 to the 2, 100 times 11 times d squared. So that's going to be 10 to the 8. So that 11 is equal to a 10. So I have, so that's 10 to 10 squared times 10 times 10 to the 8. So it's around 10 to the 11. So it's 100 billion. And we just said that GPT-3 has 175 billion parameters in it. So we got pretty close. We're off by a factor of 2. I think probably the d is, my guess is that the d is slightly larger for GPT-3. It's like 12,000 or something. But that'll get us pretty close at that point to 175 billion. Yeah. I mean, so it was trained on a huge data. And so all these parameters, every one of these 100 billion parameters has to be learned. Every single one. The model, we initialize all these numbers just randomly. Well, what the model, for one sentence, or one sequence, the model sees n times 10 to the 4. N times d is the amount of information passed into the model at any one time. It's actually a lot less than that because it's actually the number of bits that are in the words, right? Like we have a vector representation, but that vector representation itself needs to be learned. So we pass in words into the model. We pass in some number of words at a time, let's say 1,000 words at a time. Like a small essay, that's what gets passed in. Then the model does backpropagation on that. But look, the point is every single one of these 100 billion numbers needs to be learned. And the way that's learned is by processing an enormous amount of text. Any questions about that? Did people follow what happened to OpenAI last week? I mean, we almost didn't have our final projects. I was honestly pretty concerned for a little while there. Yeah, it's pretty interesting. There were rumors that, and to some extent, I don't know, rumors. Let's say that the event. For those of you who don't know, like OpenAI nearly collapsed the company last week. So the board of directors fired the CEO for very confusing reasons, or reasons that they did not actually say, just that the CEO was being misleading. And then most of the employees, like 90% of the employees, threatened to quit. And then the CEO was going to start something at Microsoft. So yeah, the company almost imploded. Then the board of directors backed down. They ended up losing to the CEO. So they all got replaced. And now the CEO is back in charge, and everyone there is happy except for a few people. But there are rumors that let me. And be complete. I'm sure you're all delighted about that. No, well, I mean, it would have been very sad if GPT-4 had been shut down. Okay, so we did that calculation. Let's see. So let's finish up the transformer equations then. So we've seen approximately what the goal of the MLP is. The goal of the MLP is to process words individually. Sort of, each word after the attention layer, each word sort of knows about its role in the sentence. It's looked at all the other words. It said, okay, here's the role that I'm playing in the sentence right now. I've gotten all the information I need from all the other words. What I need now is to be processed some more. That's what the MLP does. The MLP processes each word individually, and a lot of what it's doing amounts to recalling world knowledge from its database. Okay. Let's look more in detail, though, at what is actually happening inside of the layers, and we'll finish up basically some missing ingredients. So 2 missing ingredients so far. Do I want to? This okay. So the first one is residual connections, which is a fancy name for addition, and the second is layer norm, which is also a fancy name for something very simple. I mean, it's sort of incredible that all of these special ingredients in deep learning amounted to stuff. It's either all matrix multiplication. The MLP is literally just matrix multiplication, or it's stuff that in this case, this is like a 100-year-old idea from statistics. but they gave it its own name, and then it's like they made a major discovery. It's a very funny situation. Okay, so what happens here? So we have I'm going to just change our notation slightly, right? Like so we have a1 through an. That's the output from attention. So here's what I'll say. This is equal to attention. So we apply an attention layer to the input vectors, w1 through wn. So we're thinking about attention as a function now. Okay, attention is a function that takes in a sequence of n vectors and spits out a new sequence of n vectors. What we're then going to do is define a new sequence of vectors. We'll call them g's. So what we're going to say is that gi for I equal 1 to n is equal to wi plus ai. So this is called the residual layer. As I said, residual layer is literally just addition. So again, we're defining this new vector gi is going to equal wi, so the input to attention, the ith input to attention, plus ai, the ith output from attention. So what's this layer do? Yeah. Okay, that's a great intuition. So the original input word had like some important content there. We want to make sure it's not lost. We did attention. We want to make sure that we're keeping it around. I really like that. There's a slightly more mathematical way of thinking about what this definition is saying. What it's saying is that when we're doing attention, we're learning a difference. So we're not trying to fully recompute the representation for this word. We have the ith word. What we're going to do is, with attention, we're learning the difference between the original representation and the new representation. So this ai here is we think of this as a learned difference, or residual, between original and new representation. Okay. So again, rather than completely learning a new representation from scratch, we learn a difference between the old and new one. We may go into a little bit more depth there, but for right now, I'm going to leave it there. Okay. So we then have, let's call it ni is equal to layer norm of gi. So after doing this residual layer, which is just adding the old representation to the new one, we perform an operation called the layer norm. What is the layer norm? Let's talk about that. So the layer norm is a slightly fancy way of just taking a vector and mean centering it, that is, or centering it at 0, and then making sure it has a fixed magnitude. So what's the first thing that we're doing? So we'll talk about it. So we take a vector and we apply a layer norm to it. So here's the formula. So it's going to be x minus e of x divided by the variance of x. This is all sort of statistical language. If you've taken some statistics courses, you've learned about the mean and variance. Well, let's talk about what these quantities are. So the average value of x is equal to 1 over d. So we have a d-dimensional vector. We take the average value of all the dimensions of that vector. That's what we mean by the mean here. So we're doing this one vector at a time, looking at the mean value within that vector. There's just an average, right? So what can we say about this quantity here, x minus e of x? What do we know about this? Not necessarily, no. They could be very far away from 0. You're on the right track. What will the mean of this new vector be? 0. If we take the mean of x minus e of x, we'll get 0. Because the mean is going to be the average value of x minus the average value of the average value of x, which is the same as the average value of x. So this is a new vector with mean 0. Okay. What about the variance of x? How many people remember the definition of the variance of a vector or a distribution? When we're talking about the variance of a vector, we're treating the vector as a distribution, or it's like samples from a distribution. I'm certain all the data science majors here have seen this definition before. I suspect many others. Let's remind ourselves what the definition is. So the variance of x is equal to there's a question of whether we divide by. Let's for right now, let's just divide by d rather than like d minus 1 or something. Sorry, this should be a square root here. Sorry about that. Okay. So what's the variance telling us? telling us how basically how variable, how much on average does each position in the vector vary from the mean. That's the first thing it's telling us. But there's an even simpler interpretation here. If we ignore this 1 over d over here, okay? Let's just ignore this 1 over d term for right now. Where have you seen a formula like this before? Let's talk about how is the magnitude of a vector. Let's talk about vector y. How is the magnitude of a vector y defined? So we want to compute the size of a vector. How do we do that? Yeah. Okay, so we take all the entries in y, we square them, we sum them up, and we take the square root of that, correct? Okay. So this is a sum from I equals 1 to d of yi squared. And then we take the square root of this whole thing. This is just like, this is basically the Pythagorean theorem. So what's the relationship between this and this? And again, ignore the 1 over d out front. So let's say I'm taking the square root of the variance of x. Yes? Okay, good. So what this is doing is this is measuring the size of this vector. So the variance of x is measuring the magnitude of x minus e of x, this mean-centered vector x. So this is equal to, so we're taking the square root of this thing, so it's going to be 1 over square root of d times the square root of this thing. The square root of this thing is just the magnitude of the vector x minus e of x. So we're mean centering. So let's go back to layer norm. What's going on here? We're mean centering this vector x, and then we're dividing by the magnitude of that mean centered vector. And then we also have this additional 1 over square root of d there that we have to fill in. So what's the point of this? I mean, I'm writing out the math so that like we can eventually get to the intuition. The intuition is that we're taking what may have been a vector that may have been very large or very small, and then by dividing by the magnitude of that vector, we now make its size constant, its magnitude constant. So we're transforming an arbitrarily large or small vector into a vector of known magnitude. That's what the layer norm is doing. So what it means is that when you're passing through all these layers, the attention layer and then subsequently the MLP layer, you're not stretching out the vectors too much or making them too small. Now, there's a slight twist here, which is this is not quite the full equation. There's another scaling term that we have. People usually use Greek letters for it. We don't need to use Greek letters here. We'll just call it c. So we actually multiply this by a vector c, but it's not a dot product. We multiply each component individually, and then we add a constant that I'll call b here. And these are both learned. I mean, this is a minor detail. What these two terms are basically doing is they're just rescaling individual components of the vector in a fixed way. This does not note that b and c don't depend on x. So every vector has this applied in the same way. It just gives the model a little bit more flexibility. But like it's basically overall summary of layer norm though. One thing to take away is it's taking a vector of unknown or possibly very variable magnitude, and it's reshaping it so that it now has fixed magnitude. Any questions? Yes. Exactly. You standardize the vectors. Yes. This is something that people in statistics, like before you ever run your PCA, okay, you have to do something very similar to this. If you ever run PCA, you have to standardize your vectors. It's basically the same thing going on here. And that's like a trick that's literally 100 years old. It's a little different than what they do in PCA. But like there's this type of standardization of your data is something that occurs everywhere. And it's because the reason why you standardize is that it makes comparisons easy. You don't want to have to compare really huge vectors to really small ones, for example, when you're doing attention. So I called this thing, and here, let me go back to my previous notation. We'll actually call this A. I want to remain consistent here. So this N will become an A. So what do we do then? Oh, no, it does not. Sorry, never mind. We're going to keep using N. Okay. So we got in our original word vectors. We performed an attention layer on them. We got a new sequence of word vectors, A1 through AN. On each individual word vector, we applied this residual layer, which just means basically computing the difference between the old word vector and the new one. The attention forms that difference. We then did a layer norm on each individual vector. So now all the vectors are basically the same size. We're then going to use these new vectors, NI, and those are going to be input into the MLP. So we'll have H1 through Hn is equal to MLP of the NIs, N1 up to, well, that's unfortunate, NN. So what does the MLP do? It took in each of these individual vectors and it applied those matrices to each vector in parallel. So the vectors there don't mix. We're processing each of the vectors there in parallel. We're then going to apply exactly the same residual layer and layer norm to the output from the MLP. So let's call these new vectors B's. So we have BI is equal to what to NI plus HI. What is that saying? NI was the ith input into the MLP. So the ith word. NI is the ith word that went into the MLP. hi is the ith output from the MLP. So we're getting our new word representation for word I by summing together the old representation for word I and the MLP representation for word I. So it's just another residual layer. And then finally, we'll call them C's. Ci is equal to layer norm of the BI. So we just do another layer norm to make sure all these outputs are the same size. And this is now the transformer. At least in terms of, they're basically all the weights that need to be learned. We've introduced them. The major mathematical equations, we've introduced them. This is something that I can honestly tell you now is a transformer. There are other details that are important, but this is the transformer. Now you may ask, how was we now have actually this is like the core. This is what happens inside a transformer layer. We have the sequence of equations here. How I'm looking at this, it's like a bunch of stuff is happening. I mean, we've tried to develop some intuitions for this, but like it's happening in a very specific order. Like you first do a residual layer, then you do a layer norm, and you're sequencing that twice, and it's in between the tension and MLP. All this stuff is happening in a very specific order. How was this discovered, right? You could ask yourself that. Would be a very reasonable question. Does anyone want to make a guess about how this was discovered? Yeah, basically, they just tried a bunch of stuff, and this one happened to work. It turns out like so there are a couple of other variations in the literature that people sometimes use. So sometimes people put the layer norm before tension and before the MLP rather than after. That's a very common variation. There's a couple of variations, but to a first approximation, like there's no local change to this that you can make and still get it to work as well. It's like the local optimum. It doesn't mean that it's the best model that exists, but what it means is that there's no like straightforward modification that you can make to these equations that will not hurt things. And yeah, the way that it was discovered is just by they threw a bunch of stuff at the wall. And they were able to throw a bunch of stuff at the wall because it was discovered at Google where they had huge amounts of compute. So they were able to just call up huge computer clusters, try a bunch of stuff in parallel. They found what worked. That's where the genius came in. Yeah. I mean, so okay, it's a good question. How do you know where to look for? All of the individual components had been discovered previously. Attention was discovered in 2014 in the context of RNNs. So people first used attention for RNNs 3 years before the transformer. Residual layers were being used for vision stuff in the context of convolutional neural networks for a couple of years before that. The layer norm was quite new, but it had already been discovered. And MLPs are 70 years old. So all the individual components were there. They just yeah, I mean, there was some genius involved in like knowing what to throw at the wall, but like the exact sequence of how to order these things, that was people just guessing and then doing experiments. This is fun. There's some very important details that we still need to discuss, however. Two extremely important details. Where if you did not have these, if you don't have these details, like you still have a transformer, but what you're going to end up producing is nonsense. So let's learn about why that is. So we taken our word vectors from our initial sequence, we feed them through a transformer. And so this is not just a single layer, this is our entire transformer. And let's say we get out a sequence of vectors, I'll call them h's here. Let's just say that the full transformer, it spits out a sequence h1, h2, up to hn. And let's say that what I'm trying to do is predict the next word. That's my goal. So I'm going to be using a transformer in order to do next word prediction. Now the transformer has a very remarkable property, which is that every word was processed in parallel. Right, so I did all of these computations. I didn't have to wait until word 1 was finished processing in order to process word 2, or until the first 2 words were done to process word 3. I could just throw them all into the system at once, and then the system will output. I feed into each layer goes n vectors. Out of each layer comes n vectors. What that means is that I can simultaneously predict the next word that comes after every other word. So my target here, is to predict the sequence w2, w3, up to wn, followed by like let's just call it like end or stop. So what I'm saying here is that given the first word, my goal is to predict what word 2 is. Given the first 2 words, my goal is to predict what word 3 is. Given the first k words, my goal is to predict what word k plus 1. And I get to the very end, the final word, there's no more words to predict, so what I'm going to try to do is just predict this sequence is over. So that's what I mean by end here. Did we use EOS? Is that what we previously used to indicate the end of the sequence? I just want to make, no, maybe we haven't talked much about this. Okay. So I want to predict the final. And let's down here, let me make clear that there's wn minus 1 and hn minus 1 here. So from words 1 through n minus 1, I'm going to be trying to predict the last word, wn. Okay, any questions about this setup here? I take in each word, I'm trying to predict the next word. Transformer is remarkable because I can try to solve all these problems. I have n prediction problems I'm trying to solve, and I get to do it all at once. So how do I do that? What I'm going to do is I'm going to take each of these vectors hi, and I'm going to run them through just a linear layer. I'm going to transform each of the vectors into a vector that's the size of my vocab. So let's say that v is equal to size of my vocab. Let's define a matrix. We've seen this before, but let's remind ourselves about how this works. I'm going to define a matrix E output. So this is a V by D matrix. So then the probability for the probability distribution for next word, or for let's say for word 2, what's that equal to? It's equal to softmax of E out times H1. So E out transforms the first vector into a new vector of dimensionality V. Those give me the weights for every vocabulary item. I do a softmax. That gives me a probability distribution over every output word. So I'm going to be using H1 in order to predict what word 2 is. And hopefully I get the right answer. My loss is my normal negative log likelihood loss. In general, the probability distribution for word I, or let's say, prob for word I plus 1. So what's the word that, probability distribution for the word I plus 1, it's going to be softmax E out times which vector? How do I predict I plus 1? HI, great. So I get the probability of the correct word from this. I do negative log of that probability. I sum up all of those losses. So in my full loss function, my loss for the sequence equals the sum of loss for word I. I'm not worrying about the boundaries here. There's a little bit of fuzziness in my definition. I don't want to take up too much time though with this. So, but we have a bunch of predictions that we're making. We sum up the loss from each of those predictions. I think we know how to do that. Okay. So I mean, we've defined. Everything is defined now, right? We have n next word prediction tasks. If you give me a sequence of length n, I have n different next word prediction tasks I've defined. Predict word I that comes after all the previous I minus 1 words. I have a loss function. I have all of my formulas. I can do backpropagation. If you do this, it will be nonsense. And there are 2 reasons why it will be complete nonsense. Yeah. Well, no. I mean, there's no problem. I mean, just think about there's more than 2 weight matrices. I'm not sure exactly what you mean. There's 5 weight matrices per layer, right? There's the 3 attention matrices, 2 NLP matrices, and no, I mean, it's the same as in any MLP, right? So on problem set 3, I believe there were 2 weight matrices there, and yet you define backpropagation. It's the same exact thing. There's nothing funny about backpropagation here. Nothing technical like that. This is a conceptual error that we have made. 2 conceptual errors that we have made. Yes. Okay, well, you're absolutely on the right track here. So in attention, let's focus on attention. Let's say that I'm the first word trying to predict the second word. What information did the first word get during attention? And you smelled something fishy going on here. Yeah. All the following words. What do the following words include? Information about the second word. So if we just optimize the model as it stands, the first word will learn to pay attention to the second word. And so of course it will know how to predict the second word. It already saw it. So that's a violation of causality. I think you thought about that a little bit on problem set 4. We have now the future influencing the past. That's a big problem. So we need to fix that. There's a second problem that we're going to encounter. How is word order represented in the model right now? Let's think about the equations for attention.